Nuclear Magnetic Resonance NMR. 2023. Under the supervision of Professor Ali Salah. Presented by Abdullah Mahmoud Elgarhy. Today I will talk about the graduation project of Nuclear Magnetic Resonance, NMR, and I will review the most important points in NMR, that including Introduction to the Nuclear Magnetic Resonance, the resonance spectrum of the NMR, principles of NMR, apparatus that used in the NMR, study of the NMR spectra, causes of chemical shift in NMR, and finally the applications of the NMR. So, let's start. The introduction. Nuclear magnetic resonance, NMR, is a spectroscopy technique that focuses on the transitions between magnetic energy levels of nuclei in a molecule. It involves the magnetic energy of nuclei being placed in a magnetic field, causing them to split into two or more quantized levels due to their magnetic properties. The energy difference between magnetic quantum levels corresponds to radiation energy in the frequency range of 0.1 to 100 MHz, which is the most fundamental part of NMR spectroscopy. The three molecular parameters on which NMR depends are the shielding constant of the nuclei, the coupling constant of the nuclei, the lifetime of energy levels. And also, NMR is a more powerful tool for organic chemists to obtain structural information from the spectrum, providing information about the chemical environment of hydrogen atoms, the number of hydrogen atoms in different environments, and the structure of groups adjacent to each hydrogen atom. The resonance spectrum. NMR spectroscopy is a valuable tool for organic structure elucidation, as combined hydrogens in different bonding situations yield different radio frequency absorption spectra. This process provides information on the detailed structure and configuration of organic molecules, without revealing elemental analysis. NMR initially served as a supplement to infrared and mass spectroscopy, but now it is a more valuable tool for organic structure elucidation. Its primary function is qualitative, but current developments and improvements extend its quantitative capabilities. Nuclear magnetic resonance, NMR, is based on the interaction between radio frequency radiation and nuclei, with the primary applications being with hydrogen nuclei. The first observations of NMR signals were made by Purcell and Bloch in 1945, and their discovery led to the study of ethyl alcohol structure in 1951. The principles. Just like electrons, the nuclei of certain atoms behave as if they are spinning around their axes. When the particles in a nucleus do not have their spin paired, a resultant spin appears. The spinning nucleus produces an electric current, and has a magnetic field associated with it, and it behaves like a tiny bar magnet. Only some nuclei have magnetic properties, and so NMR spectrum is obtained only from such molecules which contain such nuclei. NMR spectroscopy is often concerned with nuclei with I equals half. Example, hydrogen 1, phosphorus 31, fluorine 19, and etc. No spectra is obtained from nuclei where I greater or equal to half. The nuclei with odd mass numbers such as hydrogen 1, phosphorus 31, fluorine 19, and etc. You should know that the nuclei of odd atomic numbers and even mass number show magnetic properties, but nuclei with even atomic number and even mass number don't show magnetic properties. The apparatus used in NMR. The apparatus consists of the following parts: sample tube, magnet, sweep generator, radio frequency generator, radio frequency receiver, and readout system. Let's begin with the first one. Sample tube. Glass tubes are durable, transparent, and inexpensive, made of chemically inert materials, typically 7 cm in length and 0.3 cm in diameter. The magnet. Permanent magnets or electromagnets provide a high-strength magnetic field with constant fields, but ancillary stabilizing devices are needed for stability. Superconducting solenoid electromagnets in liquid helium crystals are highly stable. However, the interaction of electromagnets with external magnetic fields is much less in comparison to permanent magnets. Spectrometers operating up to 100 MHz generally use permanent magnets or conventional electromagnets, with superconducting magnets requiring 230 MHz fields. The sweep generator. To make a nucleus resonate, Its process frequency must match the applied radiation frequency. When H node remains constant, the precession frequency remains fixed. To achieve resonance, the radiation frequency field must be changed, and when radiation frequency remains constant, the resonance frequency must be varied. The radio frequency generator. A radio frequency oscillator produces radio frequency radiation by wounding a coil around a sample tube, irradiating it perpendicular to the magnetic field, ensuring maximum interaction with the sample. The radio frequency receiver. Radio frequency radiations pass through a magnetized sample, undergoing absorption and dispersion. The resonance frequency can be determined by observing the absorption spectrum, while the dispersion spectrum is easier to interpret. Detection methods include the radio frequency bridge, which balances transmitter signals and allows absorption and dispersion signals to appear as an outer phase. The crossed coil method or nuclear induction method separates transmitter signals from absorption and dispersion signals. The readout system. Since the absorption signal received from radio frequency receiver is very weak, it must be considerably amplified before feeding it to a chart recorder. Study of NMR spectra. The following aspects of NMR spectrum will be studies in following discussion. Number 1. The number of signals. These give us an idea about the number of different types of protons which present in a molecule. Number 2. The positions of the signals, which tell us something about the electronic environment of each kind of proton. Number 3. The intensities of the signals, which tell us how many protons of each kind. Number 4. The splitting of a signal into several peaks. That tells us about the environment of a proton with respect to other nearby protons. Let's start with the first one, the number of signals. In a given molecule, protons with the same environment absorb at the same applied field strength, while protons with different environment absorb at different applied field strength. A set of protons having the same environment are said to be equivalent. Thus, the number of signals in the NMR spectrum will tell us about kinds of protons present in a molecule. By and large, magnetically equivalent protons are simply chemically equivalent. From the structural formula, we can easily pick out the equivalent protons which have been indicated by the same letter. Position of signals. When a molecule is placed in a magnetic field, its electrons circulate and produce magnetic fields, known as induced magnetic fields. These induced magnetic fields of electrons at the proton get oriented in such a way so as to oppose the applied magnetic field. The field felt by the proton is diminished in this way and the proton gets shielded. In the case of the induced magnetic field, of circulating by electrons about nearby nuclei, these fields may oppose or reinforce the applied magnetic fields on the protons, depending upon the location of the proton. If the induced field opposes the applied field, the proton is shielded as before, and if the induced field reinforces the applied magnetic field, the field felt by the proton is reinforced and proton is said to be DE shielded. The measurement of chemical shift. Chemical shifts can be measured with reference to NMR signal of some standard compound. The reference or the standard compound used is tetramethylsilane, TMS. A small quantity of TMS is added to the sample, while getting its NMR spectrum. Why TMS is used as a reference compound? TMS is used as a reference compound because of the following reasons. Number 1. It has 12 equivalent protons, which give an intense signal. Therefore, even a small quantity of it gives a measurable signal. Number 2. Silicon is less electronegative than carbon. Protons of TMS are, therefore, highly shielded. They give NMR signal in a region where few other protons absorb. Hence, signal of the reference compound seldom interferes with the signals from other protons. Number 3. It is inert and volatile. It can, therefore, be easily removed by evaporation after the experiment is over. Thus, advantage of using TMS as reference is that it gives a strong and sharp NMR signal in a region where only a very few kinds of other protons absorb. Causes of chemical shift. The bands in NMR spectrum are observed at different chemical shifts τ and sigma values. The cause of this difference is the different magnetic field experienced by different nuclei as a result of secondary magnetic fields associated with the molecules. The secondary fields arise due to applied magnetic field H node. The secondary field affects as when the secondary field opposes the applied field, then the effective field experienced by the nucleus is less than the applied field. In such a case called positive shielding, the resonance position moves up field in the NMR spectrum. When the secondary field reinforces the applied field, then the effective field experienced by the nucleus is more than the applied field, in this case called negative shielding, and the resonance position moves down field. The applications of NMR. There are many types from applications of NMR. I just will talk about the following types. Number 1. Identification of the organic compounds. Number 2. Determination the molecular structure. Number 3. The analytical applications. Number 4. Determination the rate of the reaction. Number 1. Identification of the organic compounds. NMR spectrum of a compound like IR spectrum serves as a fingerprint of that compound. Hence, if spectrum of the given sample is identical with the spectrum of the known compound, the sample must be identical with the given compound. Thus, the NMR spectroscopy helps in the identification of the organic compounds. Number 2. Determination the molecular structure. A large number of principles are known, which decide the structure of an unknown compound from its NMR spectrum. Some of these are outlined as follows. The number main NMR signals should be equal to the number of equivalent protons in the unknown compound. The chemical shift indicates what type of hydrogen atoms are present, example, methylene, methyl, olefins, and etc. The spin-spin splitting or multiplicity reveals about the possible arrangement of groups in the molecule. From the area of peaks, one can draw the conclusion about number of hydrogen nuclei that present in each group. Number 3. The analytical applications. NMR spectroscopy is limited to structure determinations involving nuclei with odd mass numbers, or even atomic numbers, and cannot be applied to nuclei with both even mass and even atomic numbers. It is applied primarily to liquid samples, with absorption bands for solids being too wide, and instruments not sensitive enough for gaseous samples. However, recent developments in inorganic chemistry have made it possible to observe high-resolution NMR spectra on solids, which involves high-speed sample spinning at a magic angle. This technique has been used to infer the position of silicon atoms in natured and synthetic aluminosilicates, and study molecular compounds in the solid state. Liquid sample sizes range from 0.1 to 0. For milliliters, and the choice of solvent depends. Purity, chemical stability, and volatility. The procedure is non-destructive, and can be recovered after NMR procedures. Solids cannot be determined directly with normal NMR, but they can be dissolved in a solvent or a wide-line procedure. NMR is used in the study of fats, oils, polymers, moisture contents, and gas samples. Number 4. Determination of the rate of the reaction. Certain reactions are very fast for measuring them by ordinary devices. They can be studied with the help of NMR spectroscopy. Such reactions involve a fast exchange of protons between the two reacting molecules, such as between water and acetic acid. Thanks for watching.